In this video, we're going to be talking about organic chemistry reactions. So organic reactions happen slower compared to inorganic reactions. And they usually just involve the functional groups, leaving the greater parts of the molecules relatively unchanged. There's about 8 different types of organic reactions, so we're going to go through each type and talk about how to recognize them and how to predict their products. So the first type is called substitution. So it's exactly what it sounds like. One kind of atom or group is replaced or substituted for another. In hydrocarbons, one or more hydrogens can be replaced by active members of the halogen family. This is often referred to as halogen substitution or halogenation. So here's an example. So if I have methane and I react it with diatomic chlorine, which is a member of the halogen family, I can redraw chlorine to look like this. I can show the structural diagram for chlorine. So what happens is one of the chlorines is going to replace one of the hydrogens and substitute for it. They're going to switch places. So when that happens, I'm going to make a molecule of CH3Cl. That is called chloromethane. And then the hydrogen which left is going to partner up with the chlorine, because chlorine doesn't want to be by itself, and I'm going to make HCl, or hydrochloric acid. So I've just simply substituted one of the hydrogens for one of the halogens. Next we have addition. This involves adding one or more atoms at a double bond of an unsaturated molecule. So you're just simply adding in either a hydrogen atom or another halogen. And when you do that, it results in the saturation of the compound. If you add in a halogen, it's called halogenation. If you add in hydrogen, it's called hydrogenation. So here's what it looks like. So I have a unsaturated hydrocarbon here, ethene. It's a double bonded structure. And I'm going to add diatomic chlorine. So what's going to happen is one or more of these chlorines can attack this double bond here in the middle and take up the electrons. So what's going to happen is I have both chlorines being added in at these free electrons in the middle, and the rest of the hydrogens left unchanged. So notice how I've saturated the molecule. So this was unsaturated with a double bond, and it results in a product that has only single bonds. Another kind of way to tell the difference between substitution and addition is that in substitution you always had two products. One thing swapped out for another, but it reacted with the other reactant. We ended up with two products. In addition, we only have one product. So that's one way to tell them apart. Also, substitution is always saturated compounds reacting, and addition is always unsaturated compounds reacting. So there's my product. This would be named 1,2-dichloroethane. Next reaction is fermentation. This is when enzymes produced by living organisms act as catalysts. The reactant is always sugar, and the products are always alcohol and a carbon dioxide. So this is very easy to recognize in a multiple choice question. If you see an alcohol and carbon dioxide being produced or reactant being sugar, you would have to show the enzyme on the arrow, or they'd have to use the word enzyme or catalyst in the reaction, and it's very easy to see that it's fermentation. So here is glucose. You may remember this from biology, C6H12O6. It is reacted by the enzyme zymase in yeast, and the product is C2H5OH, which is an alcohol. You see that OH functional group here. This is ethyl alcohol or ethanol. And of course we also get carbon dioxide. That's what makes the bubbles in champagne during fermentation, or that's what makes the bread rise during proofing of bread. Our next organic reaction is combustion. So in order for combustion reactions to take place, we need three things. We need an unstable hydrocarbon, so some kind of hydrogen and carbon. It could also be potentially a non-hydrocarbon, can combust as well. Some other category of organic molecule like an alcohol or an ether. We also need oxygen as one of our reactants, and we need energy to start the reaction. So here is a hydrocarbon. This is ethine, and if I react that with enough oxygen and enough energy, I can get the telltale products of a combustion reaction. In a complete combustion reaction, I would get carbon dioxide and water, and a lot of energy, which is why we do combustion reactions, to harness that energy to do work. Okay, our next reaction, and possibly the most complicated one, is esterification. So I've seen more questions on esterification than probably any other chemical reaction, maybe addition and substitution, but esterification is typically on the test, and if they ask about organic reactions, and it's typically missed. So let's try to learn what esterification is. So this is the reaction of an organic acid and an alcohol. And the two products are always an ester, hence the name esterification, and also water. So here's how esterification works. So here's my organic acid. I can tell it's an acid because of the C double bond O single bond OH functional group. And it's reacting with an alcohol. I can tell this is an alcohol because of the OH functional group. So I'm going to turn this alcohol around to show you how these pieces of the puzzle fit together to make an ester. So what happens in esterification is the H from the alcohol and the OH from the acid react, and this is where the water is coming from. And we get a dehydration synthesis reaction where we're dehydrating these molecules by taking the water out, but the bond that's left is going to come and combine with the oxygen on this side as well. So this is the reaction that produces the ester. So now I have the ester functional group here. The single bond C, double bond O, single bond O, single bond is my ester functional group. And this is methyl ethanoate. So there's the methyl group, there's the methyl part, and there's my two carbons. So there's the ethanoate because it's an ester. So there's my two products, ester and water. Okay, here's another example, just showing, it's actually the same example, it's just showing the whole thing happening at once. So the acid and the alcohol react, the hydrogens and oxygens come out and make the water, and it attaches at the oxygen in the single bond from the leftover from the alcohol to make the ester. Okay, our next reaction is saponification. This is the hydrolysis of fats by bases. So if you have a fat and you react it with a metallic hydroxide like sodium hydroxide or any other base, the products that you get are a molecule of glycerol and also soap. So saponification makes soap. This would be very difficult to draw out because fat molecules are so big structurally, it would take up a lot of room on the page. So I've never seen it actually drawn out on a Regents question, just potentially identifying it. So if they ask which of the following reactions make soap, it's saponification. It kind of sounds like soap. All right, so this is kind of a shorthand way of drawing it. So it's actually bigger than this, but this is a triglyceride. Which is like a fatty oil here. And if you react this with the sodium hydroxide, you get a molecule of glycerol, and then you get 3 soap molecules. So you make soap. Next, we have polymerization. This involves the formation of a large molecule from smaller molecules called monomers. So a polymer is just composed of many repeating units of monomers. So if you link monomers together like links of a chain, you get a much larger structure, which we now call a polymer. So you've learned about some polymers in biology. So amino acids link together to make longer and more complex proteins. Sugars are monomers that together make up bigger carbohydrates such as starch. Nucleic acids can polymerize to make DNA and RNA. And we're going to learn 2 different types of polymerization in organic reactions. So the first is a condensation polymerization. This results from the bonding of monomers by a dehydration reaction, similar to the esterification we just saw. So water is a byproduct. So here is a two reactants. These are called diols. These are like the alcohols that we learned about in our functional group video, except there's two functional groups. So we get the prefix di. So what happens is the OH from this alcohol and the H from this alcohol react to make a water molecule. So we're going to dehydrate this and we get a water molecule. And then we link the byproduct, the leftover of this molecule, with the leftover of this molecule at this O. So I end up with this. I have my C, single bond O, single bond C. And I've taken two separate molecules and linked them into one larger molecule. So there's the whole reaction together. Okay, so in addition polymerization, this results from the joining of monomers of unsaturated compounds by opening double or triple bonds in the carbon chain. So here is a molecule of ethene. This is our monomer, and if I react that with another monomer, another ethene, I can open up the double bonds here and free some electrons that can link together to make bonds to hold them together as a larger chain. So I would get a polymer of butane. So ethene and ethene could react to make polyethylene, or in this case there's only four, so it would be butane, but there's nothing stopping another ethene molecule from reacting at the other end, and I could just keep doing that over and over and over to get longer and longer chains of carbons here, and that's what's called polyethylene. So that's what we use to make things like plastics and styrofoam. So the shorthand method for this looks like this. So let me go back to that previous example. So in this one, I just showed one monomer reacting with one monomer. But like I said, in reality, there could be hundreds of thousands of these ethenes all floating together in this polymerization reaction together. So shorthand often looks like this. So they'll have the monomer of ethene in brackets and then a little n next to it. So n stands for some unknown number. It could be 2, like in our previous example, or it could be 1,000,000. It doesn't matter. I have a lot of ethenes. I have more than one. So in the shorthand, it would just look like this. So n in parentheses, your monomer, and then it just shows the saturation of that monomer. And then the n on the other side just means that this thing could go on forever. So if I had 2, it would just be 4 carbons in a row. If I had 50, it would be 50 of these CH3s in a row. So in summary here, there's 8 different organic reactions. You should recognize them by their reactants or their products. You should also be able to predict the products of any organic reaction. So the only way you can do that is by recognizing which type they are and memorizing kind of the products that they typically produce and the way that the reactants come together. So we'll be studying these in class and doing some practice problems. But if you have any questions on organic reactions, please let me know.